Hey, cool. Okay, this is some good chemistry stuff. All right, love it. Actually, let's see how that color looks. Oh, I'm going to share my screen. We're going to discuss students. I'm going to miss y'all next year. Gibbs free energy. All right, we've talked about it once, I believe. Delta G. Thermodynamic means the thermo of chemistry, the entropy, the enthalpy, the delta G. So the dynamics between heat exchange, randomness and disorder, and spontaneity. All right. Thermodynamic, once again, entropy, enthalpy, spontaneity, and kinetic control. All right. So we're going to talk about delta G, delta H, delta S. When are reactions thermodynamically favorable, meaning spontaneous, and how does that relate to kinetics? Okay. I'm going to give you some formulas. This is an important topic. Okay. You really need to understand with me. Share our screen. Let's get going. One of my favorite topics. Okay, I have a lot of favorites, but this is good stuff. I just really enjoy it. Okay, let's learn about thermodynamic favorability, free energy, all those fancy words we just talked about. I'm actually going to write down what I said the title of this is. Look, I have lines. Gibbs, I should have started doing that a long time ago. Free energy, right? That is delta G. All right, that is the energy available to do work. Work could be producing gases, expanding, a system expanding, that's doing work, all right? Moving electrons around, that's doing work. In any spontaneous process. That means a process that occurs without outside intervention. A process that you do not have to make happen. It will happen. Okay? It will happen. Now, that does not mean that it will happen quickly. Kinetics determines whether it happens quickly. Okay? Not spontaneity. Spontaneity says it will happen. If delta G for the reaction is negative, right? In any spontaneous process that occurs without outside intervention, delta G will be negative. Free energy will be lost, all right? The energy available to do work, which is free energy, right? Think about it. Free energy, it's there for you. Well, in any spontaneous process, you use some of it. Therefore, the energy available to do work decreases, and delta G is negative. Okay, I know I said a lot to just say that in any spontaneous process, the sign of delta G will be negative. If the sign of delta G is not negative, then the process will not occur in the direction written, the way it was calculated. It will not occur unless you make it happen. Just because delta G is negative, let's write that down. Let's get another color. Delta G, negative delta G, spontaneous, However, hold on, AP Chem now doesn't like the word spontaneous anymore, okay? They like thermodynamically favorable. I'll talk more about that, all right? But not right now. Let's finish that the same way we started it. Positive delta G, not spontaneous, or, excuse me, for your purposes, thermodynamically unfavorable. And we will we'll go into that. Now, just because, I'm going to go ahead and bring in that kinetics part here, because this is a perfect place to do it. Just because a process is thermodynamically favorable, that does not mean it happens quickly. Kinetics determines the rate, the speed, right, of a reaction, not thermodynamics. Okay, so just because delta G is negative, that does not mean that this process will occur quickly. Diamonds naturally form, carbon in the graphite form will turn into diamonds. Millions of years, billions of years, I don't know. Right? What does that tell us? It's got a very high activation energy. It's got a very low or high rate, no, low, constant. So, oops, right? This is determined, and speed, right, is based more on activation energy, right? Okay. And I will also say that the magnitude of K, not K, delta G, the magnitude of delta G, like if it's really, 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 really negative, then it's more spontaneous, right? So the magnitude of how negative it is relates to how spontaneous it is. It doesn't have anything to do with it being fast, okay, or slow. And you could say the same with the magnitude of it being positive. You are going to see these measured in kilojoules per mole. I don't think there's a temperature there. There might be, but what I really important is that kilojoules part, okay? Okay, let me focus. So that's Gibbs free energy. And remember, I was just talking about the topic. So let's go back up to our topic, Gibbs free energy and thermodynamic favorability. Well, what does that mean? That means we need to talk about the relationship between delta G, delta H, and delta S relationships. So let's go look at that. Actually, we are going to go look at that. But the last part of this topic, name is and kinetic control. And that's what I just brought up, right? Kinetics and spontaneity are two different things. I hope you are getting that, okay? Last thing we need to talk about, and oh, what a good topic, is something called, well, is your thermodynamic relationships. We've got delta G, delta H, and our new friend, delta S, right? Okay, let's talk about thermodynamic spontaneity. That's the relationship between the signs of all of these. I'm going to first talk about, let's talk about delta H, right? Enthalpy. What does nature favor? Does nature favor the gain of energy, which is a positive delta H, or does nature favor the loss in energy, which is a negative delta H? Well, nature favors the loss in energy. Nature likes to chill. Nature likes to relax. Nature likes stability. So nature favors a negative delta H and exothermic reaction, okay? So nature favors exothermicity. Yep, it's a word. That is more favorable. Well, when we talk about entropy, right? What does nature favor, right? What does nature favor? Well, we've got a positive delta S. I'm going to write negative delta H up there. We've got a negative delta S. This is gaining disorder. But remember, you don't use the word disorder. You say possibilities of microstates or arrangements. And this is losing disorder, which you may want to think of as becoming more ordered, right? You have to train your brain to think the right way about this because it's different, okay? Well, does nature favor your room naturally getting messy and becoming messed up and disorderly? Or does nature magically put your room back together for you? No, that requires work. So what is spontaneous here is a positive entropy, a positive delta S, okay? Because nature naturally becomes more disordered, all right? Nature does not naturally become, I like that blue. Nature, oops, wrong one. Nature does not naturally become less disordered. So what we see is in terms of our thermodynamics, we are looking for negative enthalpies and positive entropies. When that is the case, delta G will be negative, always. So what really determines the spontaneity is the relationship between enthalpy and entropy, because that is what determines Gibbs free energy. And Gibbs free energy is the ultimate determining factor with spontaneity. Okay, so in fact, delta G is equal to delta H minus T delta S. So we can use this equation to solve for delta G for a given process and determine its thermodynamic favorability simply by looking at the sign. If it's negative, yeah, it's going to happen. Does that mean it's going to happen quickly? No. It might have a very high activation energy. It may take a long time to get there. If it's positive, is it going to spontaneously occur? No, it's not going to. Okay? Now, remember, you can get delta H in several ways, but you can do the sum of the bond energies formed or the bond energies broken. So you'll often use bond energies here. This is where I hate to give you an equation, right? Bonds broken. Remember, you always have to add the delta H. Bonds formed, it's a negative, it releases the energy, right? So the difference would give us our delta H. And here we could use the delta S of the products minus that of the reactants, as we did in the last video. Actually, delta H is, I think you can use the same equation, but if you remember me teaching that, I said I like to think about it. Okay, I'm going to add this much to break the bonds. I'm going to release this much when I form the bonds. Okay, I added more than I released. It's endo. I released more than I added. It's exo. That's the way I like to do it because I don't make mistakes. Because the equation only works for certain types of data. So I'm just going to leave that at that. Obviously, your temperature here is going to be in kelvins. And realize, really importantly, I brought up This is going to be in joules per mole Kelvin, guys. And this is going to be in kilojoules per mole. So you must make units the same. All right, a lot of students, even, you know, I say it and they still don't do it. Horrible color, I'll highlight it in white. You must make units the same because they're not, and you will get the wrong exponent. It is suggested that the unit that you use, okay, is kilojoules because delta G conventionally is in kilojoules per mole of the reaction as written, okay? All right, now you could also, guys, see standard. What does that mean? That means we have standard, right? If it's a solution, it's 1.0 molar. If it's a gas, it's 1.0 atmospheres. If it's a temperature, I think it's 273 kelvins. I know at some point it changes over to 25, and that's very frustrating. Just know that, okay? All right. That's it here, guys. Okay, so you're going to have to work on your own. You're going to get very comfortable with this equation. And you're, oh no, that is not it. We need to talk some more. Now, remember up here, we said a negative delta H and a positive delta S will always yield a spontaneous reaction because it will give us a negative delta G. You can look at the math, right? If this is negative here, let's look at this mathematically speaking. If this is negative, oops, and sorry, come on, I don't want that. Okay, and this is positive, then we are having a negative value that is essentially becoming more negative because we are subtracting a positive from a negative, and this will be negative. That's what we need to finish discussing. So the way I want to write this is delta H, delta S, delta G, spontaneous. And you need to be able to create what I'm about to write for yourself. You need to be able to create this and know this, right? At the end, you need to study this so that you could create this chart on your own. Well, we said that if the enthalpy is negative and the entropy is positive, then delta G will be negative, and yes, this will be spontaneous. Therefore, if we have an endothermic, we gain energy, we become more ordered, that is both goes against nature. Nature doesn't want to gain energy and become more ordered. This doesn't happen, right? Room isn't going to just get more energy and clean itself up. No, that just will not ever happen. If we are, we gain energy, but we also become more disordered, then the sign may or may not be positive or negative. It may or may not be spontaneous. It, in fact, is temperature dependent. Let's look at an example of that. That would be like gaining energy, delta H, right? What is a phase change where something gains energy? Solid to a liquid. So let's write H2O, solid to H2O, liquid. And in this process, we have a positive delta H, and we also have a positive delta S because we have to gain energy to go from solids to liquids, and liquids have more disorder than do solids. Well, will a solid water melt? What is it dependent upon? That's right. So if the delta H is positive and the delta S is positive, we are temperature dependent. So the maybe depends on the temperature. Now you tell me, will this process occur? Oh, bad color. Will this process occur at higher or lower temperatures? Will a solid melt if we get it hotter or colder? Good. Solids melt at colder temperatures. So will become spontaneous at what temperature? Well, the solid will begin to melt at 0 degrees Celsius or 273 kelvins. If I needed to know at what temperature that would happen, delta G equals, I'm just going to leave it at that because I need to, I'll talk about that later when we talk about equilibrium. Okay, now let's finish our chart and we'll be done here. So look at the chart, right? We said first row, we have a negative delta H. We release energy, we become more disordered. Yes, that is a process that is spontaneous. However, we do not know that it will happen quickly. That is a kinetics question. If we gain energy and we lose disorder, that will not spontaneously occur. We will have a positive delta G. This will give us our negative delta G. Okay, if we have one that is favorable and one that is unfavorable, meaning delta H is positive, not favorable, but delta S is positive, which is favorable, then we may have a positive delta G or a negative delta G. If the temperature is high enough, right, it is now temperature dependent, and it will become spontaneous at 0 degrees Celsius or higher. So what we need to take from this is spontaneous at high temperatures. Okay, so the higher the temperature, the more likely it is to be, at a certain temperature, it will be spontaneous. We know what that temperature is because we know this system. Now, the last possible scenario, is that we lose energy, but we become, and we lose, sorry, that looks like a plus, and we lose disorder. Well, that is also a question mark, right? It is also temperature dependent. So let's look at a scenario and we'll finish this up. So once again, never mind. So let me change my color here. Look at this one. So what's a process, a phase change where that's not a good color, where we gain heat? Okay, well, that would be a solid to let's take the liquid to the gas this time, all right? H2O liquid to H2O gas. No, that doesn't work. That doesn't work. That's gaining heat. We're trying to lose heat. We want to be exothermic. So we are going to go from an H2O gas to H2O liquid, right? That gives us our negative delta H. And also notice we're going from a gas to a liquid, so we're losing disorder, right? And when will this happen, right? It is temperature dependent, but a gas will condense. This will occur at low temperatures, right? Become spontaneous at low temperatures, right? Because in fact, it needs to be 0 degrees Celsius or below, right? It needs to be 0 degrees Celsius or below. So what we see is where we have our question marks is that if we have a positive, we need high temperatures. You need to memorize that, but just think positive, hot. And if you have down here a negative and a negative, then it's going to occur at low temperatures. And in the next video, I'll show you how to determine what temperature that will be. You need to know this. You need to know all of this. Bye. Almost to the end, guys. Kind of sad.